So before the break, we looked at a couple of different stability criteria, right? One was a Routh-Horvitz criteria, which basically said if you have a polynomial, it's an algorithmic method to determine how many right half-plane poles you have. And then we developed a Nyquist criterion. We just went through the development of Nyquist criterion, which basically says that for a linear system, that's with a stable open loop gain, or stable loop gain, then when you close the loop, the number of encirclements of the point -1 determines the number of right half-plane poles that you have, right? We did this development. But all of that was for linear system. And we saw that you can have stable, unstable, or conditionally stable systems. So now the question is, or the question at some point was, that what if you have a nonlinearity? What if you have your system in such a way that you have a nonlinearity in the system in it? In other words, let's say, for example, you have an A, gain of A, of let's say S or j omega in the forward system, and then you have some nonlinearity in it too. It can be in the forward system or in the reverse system. You can put it anywhere you want. So right now, what we are thinking about is that you have some sort of an f, a function that comes back to the system. And what we are interested in is the question of absolute stability. So absolute stability is a little bit different from Bibo stability. Bibo stability means that for bounded input, you have to have bounded output, right? So for example, and if you go and make a quartz crystal oscillator, or an oscillator in general. You make an oscillator, right? An actual oscillator that you plug into, apply a battery to it or a power supply, and generate some sinusoidal output. Is this Bibo unstable? Is the output unbounded? The output is bounded, right? So it's Bibo stable, actually, if you think about it. A Bibo unstable system is one that grows to infinity. So absolute stability is a stricter measure of stability. It means that the output asymptotically goes to 0. So from that perspective, the orbital stability, like an oscillator, where you're in state space, you basically are going through an orbit, a closed trajectory, is considered unstable. So absolute stability means something that actually goes, eventually the energy goes to 0. Lyapunov kind of stability, sometimes called things of that sort. But anyway, so we are interested in absolute stability of something like this. And the question was at some point, what if I have this nonlinearity? So let's say this function f of whatever, f of x, let's call it just like lowercase f of x versus x. What if we knew something about this function? What if we knew that it basically, it has some shape, but it's between k1, this shape is confined between, for example, k1 and k2. Or if we know something about this, can you come up with or conjecture or propose some potential stability measure or criterion? Can you guess? It's basically just I'm asking you to guess what the stability criterion you think it would be. Or what's an intuitive one?
If it's stable, if it were linear with those extreme slopes.
So one proposal, one conjecture is that if it were stable for both of these values, if you basically replace this with this value of gain and this value of scalar gain, would it be stable? Right? Do you want to propose some other variations or some other things? Some other things that could make sense to you? Anything else? Any variations on this? What if, so if it's stable for this and stable this for that, do you know if it's going to be stable for this as well?
I guess it has to be stable
for everything in between. So that's another conjecture, right? So if it's stable for all these slopes, right? You may come back, and I may come back and say, well, how about this? But look, true, it is like this, but look at this here. If I'm around this point, the slope is even greater than k2. So from a small signal perspective, that point has even more gain. If I apply a small perturbation here, right, I'll get even more gain than K2, right? So if I kind of throw that in the mix, what would be the next conjecture?
Stable for all slopes.
For all slopes. Maybe if I look at the derivative of f of x and confine that between a range of different things, it would be stable. So good. So you guys are coming up with these famous historical conjectures. Now the first one, I guess the variation of the first one, where we say it's stable for any slope between K1 and K2. It's called Aizerman conjecture. Aizerman, Aizerman conjecture. And the second one, Aizerman's conjecture, and the second one is called the one that talks about the slope, it being stable for all the slopes. It's called Kalman's conjecture. And there's a reason that we still call them conjectures, because they are both wrong. Actually, there's a paper called the counterexample of, there are several papers called counterexample to Aizerman conjecture. And in fact, one of the problem sets that you do is the counterexample to Aizerman conjecture. And I think there's another one that's called counterexample to Kalman. I mean, it's not that hard. The systems are, you can see that you can actually have a situation, and we'll talk about some specific examples and you'll see it in your problem set, that it is, neither one of these are neither sufficient or necessary. So this is not the criterion. And people didn't know what the criterion or criteria were and conjecture things. And these are famous people. Kalman, the same Kalman filters and all those things. And they didn't do anything wrong. They say, well, this is a conjecture. They didn't say this is the answer. So maybe it is this. And it wasn't. And that's OK. And even if you say something that and then you find out that's incorrect later, as long as you don't try to hide it, you can say, well, you know what I said was incorrect, and this is the correct thing, or this is why it's incorrect, that you still get credit for it. That's how science makes progress. So what are the real criteria for evaluating the nonlinear systems and looking at them? So now let's go back to this picture again. So let's say you have an amplifier with some dynamics, and then you have a nonlinear function, and then you want to see if this system is stable in terms of absolute stability. Is it absolutely stable or not? And let's actually say that your nonlinearity is confined between, so this is x, this is f of x, is confined between some k1 and k2 slopes. So it has some shape, right? Now, if you have a nonlinearity that's confined between these things, this nonlinearity actually can have even hysteresis. So you can actually have things like this. So it can have memory. It can even be time varying. It can even change with time. So this is a pretty broad criterion. It says that if you're confined between K1 and K2, this is called the circle criterion. It says that you look at the Nyquist something like a Nyquist plot again. Okay, so you look at the real and imaginary part of, in this case, A of S, right? And you draw a circle between, so K1 is smaller, so this would be 1 over K1 would be greater. So this is negative 1 over K2 and negative 1 over K1. And you draw a circle with its center on the line. And you do your Nyquist plot, essentially. And if you do not encircle or cross the circle, you're stable. So the role of point -1 now is expanded to this entire circle. So what you did with point negative 1, you said, well, you don't want to encircle it. So now you say, this circle is the new point negative 1. But also you cannot go into it, because now, so you cannot go into the circle, or you cannot encircle. So this, what I drew here is stable or unstable based on that criterion. It's stable, right? So how about this one? That's unstable, right? How about this one? That's kind of like conditional stable. But now we know this is stable. It's like a conditionally stable system. But now this, we know that this is not going to, if you have this kind of nonlinearity, it is not going to oscillate. It's not going to become unstable. Oscillation is one kind of instability, by the way. It's not the only kind of instability. Now, how about this one? That's potentially unstable. Right. Now, this is a sufficient condition for stability. So we have to be careful about it in the following sense. It means that if you satisfy this condition, if you satisfy the circle criterion condition, you are stable, guaranteed. But if you violate it, you're not necessarily unstable. It's a sufficient condition for stability. But it's not a necessary condition. So it's a strong condition, right? It still excludes some things that may be stable, but you may say, okay, well, I don't know about this. This doesn't look good to me, but it may still be stable. But if it says, no, this is unstable, then you can be sure that it's unstable. I'm sorry, if it says, if it's something, I'm sorry, the other way. That was what I said is wrong, the last sentence. If it says something is stable, it is stable. But if it can say, well, I don't know if it's something is stable or not. Maybe it's unstable. But if it says it's something stable, if you don't violate it, it is stable, which is a useful thing if you're trying to stabilize a system. If you're trying to make an unstable system, a lot of times you are, right? When are you trying to make an unstable system? A lot of times, an oscillator. You're intentionally trying to make it unstable. To make an oscillator. I mean, there are useful unstable systems. Then it doesn't guarantee the instability. Yes, there was a question. So the blue one, it says it cannot guarantee stability for the blue one. But actually, in the case of a blue one, we know that it's unstable because it actually is unstable from a Nyquist perspective. Right? The blue one. That's a very good question you asked. But the orange one actually is, we don't know. Yes, and there's more to this, but go ahead. So
so if this was a linear system, we would essentially just have one line with slope k.
Correct. Your line with slope k would be slope 1, right? Because we are talking about basically your feedback, unity feedback, or like you're assuming that. So what this really is, the better way of, if you want to think about it in our system, in our way of thinking. So you can call this phi the nonlinear function, and then you can have your feedback, right? And this is really phi of x, if you want, well, phi of x, right? So
it scales so that any linear feedback.
Correct. So you basically just, if you had, this was your loop gain, this would, if for a perfectly linear system, this would be a straight line of x equals y equals x.
Okay.
So k would be 1. And therefore, this point becomes, both of these points, so it's confined between the line of y equals x and line of y equals x. So this point shrinks to -1. So this reduces to Nyquist criterion correctly. I didn't want to make it too complicated by adding this third one, but it essentially is what it is. But it's all fine. It's the same.
So this doesn't supersede Nyquist. So you said the orange one intersects that circle, but maybe it doesn't encircle -1 still.
So well, think about it. How could you not encircle? How could you not have the point -1 inside the circle?
Oh, I mean for the orange curve.
For the orange curve. So my assumption was that my point -1 is somewhere inside the circle. I mean, the way I've drawn it, it can be anywhere. But so, and the reason for that assumption was that assuming that basically k1 and k2 are less and greater than 1. But that's not necessarily a correct assumption. So yeah, so there's more to it. Let me just, maybe I can say a few more words and then we'll come back to it again. So by the way, what happens if your nonlinearity, you can say, you know what, my nonlinearity can go anywhere. It can be actually just flat or something like that. Or it can completely flatten at some point. So what if you have something, for example, that goes like this? This is your nonlinearity. What is k1? 0. So what if k1 is 0? What happens to this circle? Right? Because negative 1 over k1 will go to negative infinity. So this circle becomes essentially a part of a plane. It becomes a line. Right? So in that case, if you have something like that, it becomes a lot more restrictive because, say, well, it's basically just a small part of a gigantic circle. Right? So it says if you cross it to the left of that line, I don't know. I can't guarantee stability. And it's interesting because it shows you that, for example, if you have a nonlinearity like this, you may have a system that may become unstable. But if you make, for example, add a little resistor to it to make it a little bit, have a little bit of a slope, you can actually stabilize it. And it happens. A saturating nonlinearity is worse from that perspective. But this criterion is actually pretty powerful because it doesn't make any assumptions about the nature of the nonlinearity. But it's also pretty restrictive. So there's a variation on this, which is called the off-axis circle criterion. So this is a variation. So off-axis circle criterion. So this is the circle criterion. The off-axis circle criterion, which is very interesting, it says that if your nonlinearity is monotonic, so the other assumption it makes is that monotonic nonlinearity. Then it says everything the same deal, except for the fact that your circle, as long as you can find a circle that goes through those 2 points and does not cross the half part, the Nyquist part, only the half of it, right? So let's say you have something that looks like this. And let's say you have a nonlinearity that's between k1 and k2, and it's monotonic, right? If it's monotonic between k1 and k2, then it says identify those 2 points, negative 1 over k2 and negative 1 over k1. But it says any circle, if you can find any circle that you can avoid, you're good. You're stable. So can we find a circle that we can avoid? We kind of can, right? We can say this circle. You can see this is more, it gives you more information, right? It's more specific. It's a stronger condition. Because now it gives you more freedom. Because this subsumes also the axis, on-axis criterion. But for monotonic nonlinearity, it says you find any circle that satisfies this. You're good. And it's not trivial always, by the way, to find one. So for example, if my curve, instead of that one, looked like this, I don't know. Well, that still may work. Oh, I just made it work. If I were coming in like that. Coming in like that. Right? Can you find a circle that goes through both of these? Not necessarily, right? Because it may say you can do it on either side. You can try to kind of put it on this side, but I can't fit a circle here that goes through these. Because if I make it too small, then it will hit these guys, If I make it too large, I mean, that's the criterion. I'm just like trying to make qualitative examples of it.
And this is still not sufficient.
This is still not sufficient, but it's tighter. Because it allows for a lot of things that circle criterion did not allow. Well, circle criterion could not guarantee stability on certain things that this can. So there are other things that original circle criterion would have said, I don't know, I can't guarantee stability. But this guy said, no, I know. It's okay, you're good. You're stable. So this is a pretty powerful tool, actually, and not a very well-known one. So you can actually use it. So it's called off-axis circle criterion. So you have this nonlinear stuff, and then the question is that we said something interesting, though. I mean, we said that if you look at all of these pictures, I mean, if you look back at, for example, this picture, right? When we said that, according to Nyquist criterion, you can have systems that have, so when you break the loop, so this is a feedback loop, that when you break the loop at some point, and you apply a sinusoid, the sinusoid comes back exactly in phase and greater, in this case in these 2 points, 2 frequencies, but still is stable. And we said, well, we don't know what happens with nonlinearity, but now even with nonlinearity, you can actually see situations, both with circle curve, like this green curve, right? Or that purple curve. You have a situation where at these 2 points for the green curve, right, you have a system, you put a sinusoid in, sinusoid comes back in phase, larger, and still it's stable. Right? So it's actually quite a rich behavior if you think about that. So what if I wanted to make something that oscillates? What do I need to have? Because it seems that it's not sufficient to have a system that produces like a gain greater than -1, or a gain of 1 around the loop. So what is the condition? I mean, is there a condition, or is there some intuition about what makes something go and oscillate and something doesn't? So here's what needs to happen. This is, again, a necessary condition, not necessarily, not a sufficient condition. But here's one thing that could be interesting to think about. One way to think about it, again, is that if you have a feedback system with nonlinearity and everything, and then you break the loop at some point, and if you can find a waveform, not necessarily a sinusoidal waveform, in general, that you can feed to this guy, and with proper loading, so basically this is with really kind of proper loop gain calculation, right? So let's say u of x and u of y. If you can come up with a u of x, some waveform with some shape, some periodic waveform, with some arbitrary shape, that you feed into ux, and uy would be exactly the same. Not larger, not smaller, not looking different, but the same. It implies that that waveform can be sustained in the system, right? That periodic waveform. So if you can identify a general nonlinear wave, I mean, a nonlinear waveform is meaningless to say, a non-sinusoidal waveform in a nonlinear system with gain, and you can feed it in, and it comes back exactly the same, it means that you have a shot at making it possible. It's not a sufficient condition. It's a necessary condition again. And to show you that it's a necessary condition, I'm going to show you a counterexample, right? What's the counterexample? A wire. But this is a good starting point for making things that actually can sustain themselves. So you can think about it that being an infinitesimally, if you have to have an infinitesimal gain, so what comes back can be infinitesimally larger, epsilon larger. And scaled version of it by epsilon, then you would even get closer to something that satisfies it. But it's interesting because you can have a waveform, and this is one of the interesting conclusions of this, that you can have a situation where according to, you can have a plot like this. You can have a phase plot like this, right? That according to Nyquist may be stable, right? But for example, if you have a nonlinearity that looks like this, right? Let's say this is point -1. If you have a nonlinearity like this, would so K1 is 0, right? And let's say K2 is 1. If you have a nonlinearity like this, would the circle criterion guarantee stability? No, right? Because what would the forbidden region for circle criterion be? A line to the left of this, right? So you are clearly going in there. Would the off-axis circle criterion allow it? Because what would the off-axis circle criterion become if you make K1? Because basically means that if you can pass a line, if you can pass a straight line, that's what off-axis circle criterion becomes. So if you can pass any line through the point -1, in this case, that would not cross this line, you're good. Can we find the line? Well, in this case, I think we can. Right, you can find this line. But there are situations where you can actually cannot. Right? If I was coming in like that. Now, and the off-axis would not allow it. So what happens is that you can actually, so it says that it may be possible to have a system whose phase never, in the Bode plot, its phase never crosses the 180. So if you look at the Bode plot of something, it's a phase that never crosses the -180. And with nonlinearity, you can actually make this unstable. And that's, in fact, one of the counterexamples of the Aizerman conjecture. And you can have it, and this is one of your problem sets. You have a system whose phase never goes to, it never has a phase of 180 or 360 around the loop. Or its loop gain has never a phase of -180. And with the right nonlinearity, actually, it starts oscillating. It becomes unstable. So you can see that it's pretty sophisticated, complicated, and not complicated, but sophisticated. But this viewpoint of a waveform that can regenerate itself is probably the closest intuitive thing that you can come up with. And can be an epsilon greater than itself when it comes back, that would allow you to kind of give you some guidance about how that works. So any questions?